All right, another hello from West Virginia. Oh, I am definitely not in West Virginia. But what I definitely have is joke of the day, and I know you're ready for it, so let's get to it. What kind of music did the Pilgrims like? You know, the Pilgrims that came over on the Mayflower? What kind of music did they like? Well, Plymouth Rock. Aren't these jokes of the day great? I love these. We're going to rock our way now into solving systems of linear equations by substitution. In a previous video, we looked at how to solve our systems of linear equations by graphing. And remember, we decided that your system is a set of two equations. And in order to find that solution, you're looking for a common solution to your system. And that common solution is going to be the intersection of the graphs. Well, you probably noticed in the first example that I did, it was a little bit tricky in order to be able to find that point of intersection because I was dealing with some fractions and it was a little bit challenging. In addition, I did 3 examples, and every example that I did, I said, here's hoping my lines are straight. I'm not very good at drawing a straight line. So sometimes that method of graphing can get a little bit tricky. Well, we have 2 other methods for solving our systems of equations that alleviate that trickiness and that uncertainty with the graphs. And we're going to look at the first of those 2 methods, which is called the method of substitution. Now, mathematicians are not creative at all. We call it like we see it. So if it's called a method of substitution, probably what's going to happen? Yeah, we're going to do some substituting. So what happens here is, and let me flip this over to the examples to give you a general idea of what's going to happen. The point of the method of substitution is to be able to take one of the 2 equations and substitute it into the other equation. That's the crux of the method of substitution. So as I look at these 2 equations and I'm saying I've got to be able to substitute one into the other, the only way to make a substitution is to have a variable completely by itself. So if I said x equals something, then whatever that something is, I can plug it in wherever I see an x. Or this, by the same token, if I see y equals something, whatever that is, something is, I can plug it in where I see the y. So in order to make that method of substitution happen, I need to take one of those equations and get one of the variables by itself. Now, folks, it does not matter at all which equation that you get by, which equation you work with, and it doesn't matter which variable you get by itself. So make your job easy and pick the easy one. But let's flip back to those steps. So if we're going to make a substitution happen, then what that means is I'm going to solve one equation for one variable. And like I said, it really doesn't matter which one I work with. Pick the one that's easiest to get a variable by itself. So let's flip back to that first example. And since it doesn't matter which equation I work with, I'm going to pick the top one because it'll be easiest to get a variable by itself. And like I said, it doesn't matter which variable you get by itself. So what I'm going to do then is I'm going to get that x by itself, and in order to do that, I'm going to subtract that y. And now remember, this tells me x is all of this. So if x is all of this, I should be able to take all of this and plug it in wherever I see an x. Now here's the catch. I need to make that substitution into the other equation. If I substitute this back into this equation, I'm only working with one equation. I need to work with the system. So I need to be able to work with both equations. So I'm going to substitute this into the other equation where I see an x. Now let me go back to those steps again. So we have solved one equation for one variable, and now what we're going to do is substitute this expression into the other equation. That is critically important, so I'm putting it in all caps. Into the other equation. Now notice that when I do that, and we'll flip back around to that example again. Notice that when I do that, it was 3 times x, but now it's going to be 3 times all of this negative y plus 4. Now I've got my minus 2y equals 7 from the equation. But what do you notice here? How many types of variables do we have? We only have one. Granted, there's a y here and a y here, but it's one variable. When you have one variable, can you solve for that one variable? Oh yes, you most definitely can. So in order to solve for that one variable, I'm going to distribute my 3 through. And then I'm going to combine up my like terms. A negative 3y minus 2y will be a negative 5y. And then I'm going to slide all my constants over to the other side and subtract 12 from both sides. Now when I do that, I get a negative 5y equal to a negative 5, and I'm going to divide both sides by 5, giving me y equals 1. So let's flip back to those steps. When we substitute that expression into the other equation, we have an equation that we can solve for the remaining variable. Solve this new equation for the remaining variable. In that case, we saw that we were solving it for y. Now we're going to skip over what's in brown and orange, and we're going to jump down to here. So once we solve it for that remaining variable, and we know that the y is going to be a 1, now remember, I'm looking for the point of intersection for these two lines. The point of intersection is going to have two coordinates. Now what I know about the coordinates is that the y coordinate is 1, but I need the x coordinate. How am I going to get the x coordinate? Well, like we said before, if I know that the y is 1, then that means I should be able to take that 1 and I should be able to plug it in where I see a y. So I can plug it in here, here, or here. And it doesn't matter where I plug it in. I used to always say I had to go back to these originals and I couldn't substitute it in this one because I thought, well, what if it's wrong? But if I did this incorrectly, that's not even going to be right. So it really doesn't matter where you substitute it. But as a habit, I do still tend to want to go back to one of the very original equations. So I'm going to plug this 1 right in here. When I do, I get x plus 1 equals 4. I'm going to subtract that 1. That's going to give me x equals 3. So now I know that the point of intersection is 3, 1. And that is my solution to the system. So let's flip back then to those steps. And like I said, we're going to skip over the brown and the orange. We're going to see that in the next two examples. We're going to skip right down here. So once we've solved it for that remaining variable, we're going to substitute that. Substitute into the original equation and solve for the other variable. Now we need to remember that this solution is a set, and you saw that I did put it in braces, but remember this is a solution to the system. If it's a solution to the system, then that means it's a common solution, and that means it should be a solution to both equations. So it is critically important that we check the solution in both equations. And that's in all caps. Notice the exclamation points. Critically important. We check it in both equations because it is possible that this is a solution to one equation, but it's not a solution to the other equation. In order for it to be a solution to the system, it needs to be a solution to both. So if I take this 3 and plug it in here for x, and take this 1 and plug it in here for y, 3 plus 1 is 4. Yep, it works in the top one. Let's check it in the bottom one. Plug the 3 in here. 3 times 3 is 9. Plug the 1 in here. 2 times 1 is 2. 9 minus 2, yep, 7. So this is in fact a solution to the system. Okay, so this is how the method of substitution works. Like I said, take one equation, get one of the variables by itself, substitute that into the other equation. Never substitute back into the one you were already working with because this needs to work for the system. So let's go with that. Let's take a look at this next example. Notice here, half of our work is done. Yes, I love it when that happens. In the top equation, one of the variables is already by itself. So I'm going to go ahead and take this, and this says x is all of this stuff. So that means everywhere I see an x, I should be able to put this stuff in there. Always substitute into the other equation. So I'm going to substitute this down into this equation. It was 12 times x. Now it's going to be 12 times all that stuff. Now, don't freak out about the fractions. They tend to work themselves out, so don't have a heart attack when the fractions are there. But once again, notice I only have one variable. When I have one variable, I can solve this. I'm good. Now remember, I'm going to distribute my 12 through the parentheses and all the way through the parentheses. And right here when I multiply those fractions, oh yeah, we still got that going on. We're going to cancel those diagonals and then we're going to shoot straight across. Still, that math gang is happening. So when we cancel in these diagonals, 3 goes into 3 once, 3 goes into 12 4 times, I'm left with a 4y. Now 12 times negative 6 is a negative 72. And notice here that I'm at the point where I can combine up my like terms. Well, 4y minus 4y cancels out. I'm left with negative 72 plus 24. Well, negative 72 plus 24 is a negative 48. Now, we have a little bit of a heart attack because the variable's gone and we go, oh my gosh, the variable can't go away. We have to have a variable. It's okay for the variable to be gone. We've seen stuff like this before when we were just solving basic equations. Remember when we solved basic equations and the variable was gone, we said, okay, that either means I have no solution or everything works, every real number works. Now, similar idea here, but let's think about what's happening. I'm looking at a 2D coordinate plane because I can graph this equation on the 2D coordinate plane. I can graph this equation on the 2D coordinate plane, and I am looking for a point of intersection. So I have to be careful about what's happening here. But like I said, the bottom line is that I'm looking at this, and when the variable's gone and I go back and I double check my work, I did everything right, I'm fine. So I need to decide, is this a true statement or a false statement? That should ring a bell. Yeah, we've done that before. This is a false statement. Now go back to when we were working with those basic equations. When we came up with a false statement, what worked? Remembering, what we're looking for is what can we plug in here and create truth. Truth is going to be what we plug in here and here. I get the same thing on both sides. And for it to be a solution to the system, I'm going to plug it in here and here, do that order of operations, and come up with a 0. It's going to work in both equations to create truth. So when this happens and I have a false statement, what can I plug in there and create truth? You're right, nothing works. So like we had seen before, this means I have no solution. And you saw that in the previous video when we were solving our systems by graphing. Remember when we were graphing and we came up with no solutions, what did that mean about the lines? Yes, we have parallel lines. Remember, they're going to be parallel because I'm looking for a point of intersection for that system. And if I don't have a point of intersection, that means they have to be parallel lines. So this is a system of parallel lines, and the bottom line is this: what is my solution? I don't have one. So let's flip over here now, and let's take a look at the orange set here. With the orange set, we are looking at a situation, the orange set. We are looking at a situation when both variables are eliminated. The resulting equation is a contradiction. A contradiction. And a contradiction simply means that we had a false statement. And we said, okay, when it's false, we have parallel lines because we have no solutions. And remember, how do we express that solution set? Well, one way is to say the set, because remember, braces indicate set, and we want the set to be empty, so we're not going to put anything in it. Or the other way to express it is to use that null set. Both of them mean the very same thing, and like I illustrated in the previous video, what you definitely don't want to do is do the set with the empty set inside of it, because that's a set with a set. That's not what we're indicating. We're indicating one set that's empty, and either one of these indicates that, this does not. So now let's flip back to those examples one more time. And remember, with the method of substitution, that means I'm going to substitute one equation into the other one, and it doesn't matter which equation that I'm working with, and it doesn't matter which variable I get by itself. So as you look at these two, which one do you think is going to be the easiest one to get a variable by itself? Oh, yes, absolutely, that bottom one. Now the question is, which variable do you think will be the easiest to get by itself? Absolutely. Let's get that y by itself, because all I have to do is take that thing and divide by 6 on every single term. Remember, that's the beauty, is that it doesn't matter which equation that you decide to rearrange, and it doesn't matter which variable that you decide to get by itself. Make your job easy. So when I divide through by 6, that definitely gets that y by itself. And notice that when I take 16 and divide it by 6, that fraction simplifies because both numerator and denominator are divisible by 2. And then when I reduce that 4 over 6, it simplifies as well because both numerator and denominator are again divisible by 2. So that puts the y by itself. And remember, what that means is y is all of this stuff. So that means I should be able to take all this stuff and plug it in everywhere I see a y. Now remember, don't plug it back into the equation you just rearranged, because you're working with the system. If you plug it back into the one you just rearranged, you're not working with the system. So I'm going to plug it into the other one where I see a y. So it was 2x plus 3y. Now it's going to be 2x plus 3 times all this stuff. Now, you may be having a heart attack because there's some fractions in there, but remember, don't worry about the fractions. They tend to work themselves out. So yet again, I'm down to one variable, and when there's one variable, I can solve this. So we know that we're going to distribute that 3 through, and remember, when we distribute, we're multiplying those fractions. There it is again. We're going to cancel on those diagonals, and then we're going to shoot straight across. So remember I said not to worry about the fractions? These 3's will cancel out completely, and I will be left with an 8. And then when I distribute here, once again canceling on those diagonals, the 3's will cancel out, and I'm left with a negative 2x. And so now I'm ready to combine up those like terms, and 2x minus 2x, they cancel each other out. I am left with an 8, and I have a heart attack. Give me my smelling salts because the variable is gone. But remember, don't have that heart attack. Double check your work. We did everything correctly. This is where we look at that statement like we did in the previous one, where we discovered that it was a false statement because a negative 48 is definitely not a 0. That is no way true. But this is true because it says 8 is 8, and 8 is always going to be 8. And just like we said before in the previous one, when we said, now wait a minute, we are trying to figure out what we can plug in here and create truth. Similarly down here, what can we plug in here and create truth? Well, let's think about what happened. Here, when it was a false statement, that meant there was nothing that we could plug in and create truth. Also remembering that we are looking for the solution to the system, and when we're talking about this system, remember, I'm looking at graphs. I'm looking at the intersection of the graphs. And so I'm looking at lines in the 2D coordinate plane. In this case, remember, they were parallel lines because there was no solution. Now here, when it's true, what happens is I graph this line, and it may go like this, but then when I graph this one, it's going to fall right on top of it, because true statement means they are the same line. We discussed that back here. Actually, we didn't discuss that back here. We're getting ready to discuss that back here. But this means that I have they are the same line when it's a true statement. So we would need to recall, go back to when we were working with those basic equations. The basic equations, now we got to be careful here, because with the basic equations, we said, okay, when we came up with a true statement, we said that meant all real numbers. But all real numbers literally means every single number you can think of. Now keep in mind here that we are looking at the 2D coordinate plane, and we're putting lines in the 2D coordinate plane. So what's happening here is, when there's my x-axis, or sorry, my y-axis, and here's my x-axis, and here's the graph. So we got to think about this. When we say all real numbers, we're meaning literally every number in this 2D coordinate plane. You know that's not what the solutions are. The solutions are what are on these lines. The solutions are the points on those lines. So therefore, I can't say all real numbers like we used to say when it was a basic equation. That's not going to work here. But what I do want to say is, it's going to be every single point on this line. And remember how we discussed it in the previous video. How do we say every single point on the line? Well, remember we said we're going to use braces because braces indicate set. And we're going to say the set of all points. That's why we have that generic XY sitting there, the set of all points. That satisfy, that's what the colon means, and we're going to pick either of these two equations. And it doesn't matter which one we pick because they both represent the very same line. As a habit, I tend to pick the top one, but it really does not matter which one you pick because they both mean the very same line. So here's my solution, and again, what this says is the set of all points that satisfy that equation, because those are the ones that are on that line. So let's flip back to those notes and let's fill in the rest of it. Looking at the brown part here, part A, and notice that once again what it says is if both variables are eliminated, then the resulting equation is an identity, meaning that it's true. That's what we just saw. We saw an identity. It was a true statement. We did eliminate both of the variables. And remember, when we have an identity and it's a true statement, then what that's going to indicate is that we have same line. Now, how many solutions are there when you have the same line? Remember, lines go on forever in both directions, so you're going to have infinitely many solutions. But now that only tells me how many I have. I need to know what are those solutions. It's every point on the line. And like I just said, the way that we express that is we use braces to mean set. We're going to use the generic x, y. So this is the set of all points that satisfy. And we're just going to pick one of the equations. And it doesn't matter which one we fill in here because they both are the very same line. So hopefully this helps you with solving your systems of linear equations with that method of substitution. And like I said, what happens here is you're still looking for that common solution, but the way you go about it is a little bit easier because you don't have to graph the lines. The mathematicians are not creative. We call it like we see it. So if it's a method of substitution, we're substituting one equation into the other. So you get one of those variables by itself, substitute it into the other equation, solve that for that variable, take that answer, plug it back in, substitute it back in to find out what the other variable is. And like I said, if you wipe out all the variables and you have a true statement, same line, here's how you express the solutions. But if you wipe out all the variables and you have a false statement, you have parallel lines. You don't have any solutions. So you either express it with your empty set like this or your empty set like this. I hope that helps. Have a great day.